Bueno, muchas gracias por vuestra asistencia. A continuación, el profesor Resdar nos va a hablar sobre, bueno, nos va a dar una charla titulada Using Field
to construct P-groups. To construct finite P-groups.
Okay, thank you very much, and I will talk in English.
Okay.
Well, so let me begin just with some notation. So P is going to be a prime. Is that right? Can you see that or not? Yeah. And N is going to be a positive integer. And then F is a field of order P to the N. And then if you have such a field, I want to talk about how you can use fields like this to describe small P groups. And one thing, immediately which you can associate with this field is something which I sometimes call the semi-affine group. So we get a group G, which is a product of three subgroups, where A is the automorphism group of the field. So that's a cyclic group, so it's generated by this little a, and it is cyclic of order n, the power of the prime. And B is the that's bound to happen. E is the multiplicative group of the field, which is also cyclic, and which is cyclic of order and is cyclic order P to the N minus 1. The multiplicative group of the field is a cyclic group of this order. And A acts on B just as it does in the field, so that B conjugated by A is just B to the P. So this is a metabelian group with a, this is cyclic of order n, with a group of order n acting on this group of order P to the N minus 1. And then you can put a C at the bottom, so C, which is the additive group of the field. So that is it's an elementary abelian group of order P to the N. So it has N generators, each of order P. And in fact, so I think so. This is C, which I should probably not use very much. C is a multiplicative group, right? Because it has these cyclic, but it corresponds to, there is what I call W, which is also the additive group of the field, but written additively. So it's generated by W1, Wn, and that is equal to kind of, well, it's the additive group, so I'll call it CP again, but it's additive, CP, direct sum, it's a direct sum of again P copies of this. So W is the additive form of C, and so you have an isomorphism for theta, which I should call theta from W to C, is an isomorphism. And then, for example, so U to the theta times V to theta. So U and V are supposed to be in W, and so when you multiply them in W, that corresponds to adding them when you multiply them in C, that corresponds to adding them in W. And similarly, A and B act on C or in W, but so if you take an element of W and you take the image in C and you act on it with A, that is the same as taking the pth power of W and then mapping that back into C. And similarly, W to the theta B is the same as multiplying by this element little b. And so the net effect is that you have this group G, which is the product of these three groups, A, B, and C. And so the order is, well, A has order n, B has order p to the n minus 1, and C has order p to the n. So it has these two, so the groups are all abelian. This one is elementary abelian. This one is cyclic and acts on it. And this one is also cyclic and acts on the other two. And so that's this is a remarkable group, really. It's surprising that that these two are so big, or they're nearly equal. And then you have this automorphism which acts on the two of them. Now, what else was I going to say about that? Yes, another remark about that, as I said, you could, so in other words, W is an sort of FP AB module. So W is the additive form of C, and so I can think of it as a module for A and B. And this has the property that if B1 is a subgroup of B, and W is FPB B1 irreducible or simple, so B1 is big enough so that W has no B1 submodule, so simple I should call that. Then what is true, I'm not going to say why it's true, then the automorphism group of B1W or B1C, whichever way you want to call it, I shall tend to mention W, but it's really C which is there, I suppose. So the automorphism group is actually the group ABC, so it's the group G, which is A, B, and C. And it's kind of easy, it's kind of plausible, I think, because the B1 kind of determines how the it multiplies W, so it kind of determines the multiplication in the field, more or less. Now, I shan't really mention this again, but this is kind of the bottom of some of the things I'm going to say later. But I won't, because I'll be interested later on in automorphism groups of groups. Now, I'm interested also in, so I have this group ABC or ABW if you like, this is the group at the bottom is this elementary abelian group of order p to the n, and I would like to make that into a non-abelian group. I'd like to put something else underneath that, well, really for the following reason. You may remember that, yes, right. So let me remind you of a couple of definitions. So if P is a P group, so P is always a prime, so little p is always a prime, with the P powers in P contained in the derived group P dashed, and the derived group is the center of P, and it's cyclic of order P. So I just put I have a group like this W or the C, and I just put underneath it a cyclic group of order P. And that is called an extra special group, then P is extra special. And they are very useful for the following reason. There's this lemma of Hall and Higman, which says, I'm not going to write down what it says, but what it means is the following: that if you're in a soluble group, like all the groups are soluble, it's never going to be any group which is not soluble. So if you have a soluble group and you're trying to prove something, which you are pretty sure is true probably, right? And so you take a minimal counterexample, and then very often, or nearly always, there will be somewhere near the bottom of that minimal counterexample, there will be an extra special group and something like a cyclic group acting on it. So that's really the reason why these extra special groups are useful or important or something. So in a minimal counterexample, let's say this again. A minimal counterexample. So a minimal counterexample often, in fact nearly always, contains a subgroup like kind of B1P, where B1 is like the B1 I had a minute ago, where B1 is cyclic and P is extra special. Where it's cyclic and P is extra special. And in fact, the interest, what I'm going to talk about is kind of joint work with Arne Feldman and Maria Dolores, and this is exactly that situation that we came across. We were trying to prove something about fitting classes and so on, which I won't go into at all, but there was a minimal counterexample, and there was a subgroup just like this at the bottom of it. And so we wanted to say what those groups could look like. Now, as well as what do I want? Oh, here it is. And the way that we came up with was to make the situation even more complicated, possibly, and that is to define a group, what I call a Kaminer group. So now a Kaminer group, or Kaminer P group, I should say.
Do you want
to remove the light?
Maybe. Yeah. Can I? Yeah. I mean, is it? Can you still see it with the light on, without the light?
Okay.
Yes.
Now, is it all right for you or not?
Yes.
Can you see? Yeah. Okay. All right. Yeah. It may be better. I don't know. So a Kaminer P group, P satisfies the following thing, that if G, if you have an element of P outside the derived group, that always implies that every element of the derived group can be written as a commutator of the form Gx, where x is in P. So if you take you fix an element outside the commutator subgroup, and you require that every element of the derived group should appear not just as a product of commutators, but actually as a commutator with this particular element G. Now that's a very peculiar, Kaminer actually defined, Kaminer is an English mathematician, about a bit older than me, similar age to me, and he defined something a little bit more general, which I won't mention what it is, and I think it was something to do with representation theory, which also I won't go into at all, so never mind that. So that's another point which actually is not too difficult to see, that something which is equivalent to this statement is that if G is in P minus P dash, that implies that the centralizer in P of G, or rather the order of that centralizer, is the index of the derived group. So that's perhaps a more definite way of saying it, and it's not difficult to see that these two are actually equivalent to each other. Because once you, anything which is outside the commutator gives you distinct, anything which is outside the centralizer gives you distinct commutators, and this just forces, this forces the distinct commutators to fill the whole of P. Now, and the point about this is that first of all, an extra special group is always a Kaminer group. That's easy to see. And secondly, that if you have a Kaminer group, then you can get an extra special group from it. So if P is Kaminer and I'll call it Z is less than P dashed, Z is less than P dashed, and P dashed. In fact, let's take this. Let's start again with that. I'm going to use the notation P sub anything, or P sub 3 will be the third term of the lower central series of P. Right, so this is kind of gamma 3 of P is what it might be called, or K3 of P, right? And that will do for different numbers as well, if I come on later. So if P3 is the gamma 3, and you take so something a Z which is contained in that and less than P dashed, and P dashed over Z equals P. So you have a subgroup between gamma 3 and P dashed, which is of index P in P dashed. Then it's easy to see that that what you have, that P over Z, implies that P over Z is extra special. So this is a way of kind of getting at an extra special group. You can by starting with a Kaminer group. Now you may think that's a silly thing to do because Kaminer groups are much more complicated than extra special groups. But nevertheless, anyway, right, that's what I shall do. Yes. Now there's a Kaminer groups have been studied, but there are. I want to quote some results about Kaminer groups, which were found out. The first person to as I said, Kaminer was thinking about representation theory, so that he just defined them more or less, didn't do much else with them. The next thing was a man called MacDonald, wrote a couple of papers looking into the properties of these Kaminer groups. So I want to state some of the results he's got, and I want to. This is also Veradi as well. Let me rub that out and start and say something else first. Let me give a very easy and well-known example of a Kaminer group. So this is an example. So let's take, I shall denote it by x, y, z. So x, y, z will denote a matrix. So in the general linear, the 3 by 3 matrices over F, well, over any field, indeed, over F, over the field which I started with. Then, as I'm sure you all know, if you multiply, this is really just the notation that I want to bring this in. If you take two of these elements, these elements form the Z of P subgroup. of this general linear group. And if you multiply two of them together, let me just copy it down so that I don't make less chance of making a mistake. It is it's equal to a plus x, b plus y, and c plus z plus, let me get it the right way around, plus ay, I think. And then what I also be interested in are the commutators of these things. AC. So that's then, it's the two first coordinates are 0, the x and the y coordinates are 0, and this one is a y minus bx. And this group, which I shall call P sub f, if I remember to call it anything. So P sub f is the set of these x, y, z, which are just these matrices, these things where x, y, and z are in F. So that is a Kaminer group. So that's just an example of a Kaminer group, just to fix your minds. It's easy, and it's very easy to see it's a Kaminer group. So I won't go into that. But now let me go back to what I started saying before. So note. So these are these results of Donald and a man called an Italian mathematician called Verardi.
Sorry, this example is a extra special group also?
Well, it's not extra special because the third thing is not of order P, but it's a Kaminer group, so you can get an extra special group by factoring out everything. You see, this has order P to the 3n. I mean, if F is of order P to the n, then this group has order P to the 3n. Because there are three different elements of the field there. But so it's a Kaminer group, and again, by this method down here, you can get an extra special group by factoring out something in the z part, which is of index p. All right. So now there are various. I want to state some facts about Kaminer groups, which follow from this definition here, and which I'm not going to prove. And they're not always. Sometimes they're easy to prove, sometimes they're not. So suppose P is Kaminer and P dashed is not equal to 1. So that's kind of rule out the trivial case there. P dashed is 1 would be silly. And then, first of all, P to the P is contained in P dash. So in other words, the P over P dash is elementary abelian. Now that's not particularly easy to prove, but it's true, right? As I said, it's really these are quite stringent conditions, right? These are rather and a bit complicated to understand what they imply. But they imply that P to the P is contained in P dash. And what they also imply is that in fact, yes, this you can see, as I said, once you have a Kaminer group, you can easily get an extra special group. Now, an extra special group, the P over P dash has even degree. Now, so in particular, that will apply to Kaminer groups. And so the order of P over P dashed, which, as I said, is elementary abelian because of this thing, is, I will call it P to the 2n. I'm sorry, that's a different n, I'm afraid, than we had before. No, it isn't actually. It's the same n as we had before. But so it's even anyway. It has to be even. And the other thing which you can get is that the order of P dashed over P3, there's a bound on that as well. That is less than or equal to little p to the n. It has to have at most half the dimension of the top bit thing. Okay? And again, this follows from this 1 and 2. that's perhaps not so difficult, but this is a bit, well, no, yeah. Or rather the fact that p to the p is contained in p dash. I mean, it's actually, it's a nice proof, but it's not immediately obvious, but it's not all that hard to do. Now, so I would like to construct Kaminer groups in order to get at extra special groups, I suppose, really. Right? So now let's have a construction. This is a construction. So both W and Z, Z are vector spaces. Over the field of order P. And W is going to be the P over P dashed, and Z is going to be the P dashed, right? Z is going to be so. So then I form a set. P equals P equals W. So it's the kind of the Cartesian product of what's it called? So it's the set which consists of a pair, so of W and elements of Z. And I suppose that I have a map from W cross W to Z is bi-additive. By which I mean that, so F, there's two elements out of W, and if you have X plus A plus X in the first entity, then you get F with the A and F with the X, all right? So that is to say, F of A plus X and B is F of AB plus F of XB. And a similar thing with the B, all right? So that's what I mean by bi-additive. And then in that situation, and you define AX and BY. In fact, let me stick with the notation I have, which is not quite that. Now I call it U, not A. So let me stick with that. So it's U, X, and BY is U plus V and X plus Y plus F of U and V. And so I have now a product on this P, on this W cross Z, and what I'm telling you now is that that is a group. That makes W cross Z into a group. So P equals W cross Z is a group. And if I take the commutator of two of these things, Ux and Vy, that is 0 and F of U and V, F of U, V minus F of V and U. So it's like what happened over here, except now we have this map F doing that. Okay. And so this is a kind of a very, I mean, all I want is that F to be bi-additive. So there's not much of a restriction. Well, there's a restriction on F, but it's still quite general, and it's perhaps slightly remarkable that for example, the associative law follows from this. But it's very, if you can check that very easily, it does follow. It just depends on the fact this is bi-additive, but that is giving you the commutator. Now let me. I'm now going to introduce the field a bit more now to have some. So this is where we come to kind of calculating in the field. So let's take F to be this F P to the N, like it was in the field, the finite field of order P to the N. And then what am I going to do? Is I'm going to define two maps, sigma and tau, from F to, well, let me be a bit more precise. So sigma goes from F to F, and tau, which goes from F to the subfield of order P, which is in the field of order P, which is inside. And tau is just going to be the trace. So I see, let me, yes, no, sorry, no. I wanted to make it, yeah, let me start again. So let's, as I said, n has now become 2n. So let's take the field of order 2n, and I map from the field into the field of order n of half the dimension. Okay? And so tau is going to be the trace map. Tau of x is going to be x plus x to the p to the n. Right, so that's a familiar map in the theory of fields, you're in this smaller field. You're in this field of half the dimension, and sigma is sigma of x in the same way is going to be x minus x to the p to the n. And if you that's why I want. Yeah, I haven't said this already, but I want p to be odd, because otherwise these will be the same. These two will be the same. This whole thing will collapse. So let's take p odd, p different from 2. And then it's easy to see that these are that for example the image of tau is the kernel of sigma, and the image of sigma is the kernel of tau. So these things kind of complement each other. And that's very easy to see, in fact. And what I'm going to do is I'm going to take my W is going to be the F plus. So this is F order P to the 2n on the top. And my Z is going to be the image of sigma, or the kernel of tau, whichever way you want to say it, the image of sigma. And then I'm going to take my P is W cross Z, just as I did a minute ago on the other side. And then I'm going to define the F. I want to define this this biadditive map, okay? And that's going to depend on the theory of fields, on the fact that operating in these finite fields is so let me write that. So I'm going to take F of U and V is going to be, well, I'm going to put in a half, because P is not 2, I can divide by 2. I think I could leave it out and it wouldn't make much difference, but let me put it in, since that's what we did before. And so that's going to be sigma of U times V to the P to the N. So when I take the product of the elements, so these elements out of the big field, right? These are U, V are in F, which is the field of order P to the 2n. And so I'm going to take, so this is, I apply a field automorphism to V, and I multiply them together, and then I apply sigma to them. So I then get into this, the kernel, well, into the kernel of tau, if you like, into whatever the kernel of tau is. And then I did make this, define P as above, so P as above. Yes, I don't know if I want to, yes, perhaps I'll go with it. I'll do a bit more calculation, I'm afraid now. So let's, what do I want to take now? Yeah, so P as above is a Camilla group. And that's really because, yes, because the commutator, as I have this, so the commutator of U x and V y in fact, let me write it down a bit more explicitly now. Let's take the product of those two elements to begin with. So ux times vy. So this is just this formula over here with a particular function f is then u plus v, and then x plus y plus a half of sigma of u v to the p to the n. Right, so there's a very definite formula anyway, which you can work with, which is the thing which I'm interested in. And then you can work out then what is the and then the commutator of the two things, ux and uy. The first entry is 0, and the second entry is the kind of the different, is as it was before. It's this thing minus the thing with u and v interchange. So it's a half of sigma of u times e to the n minus sigma of u to the p to the n times v, which is what happens when you apply, when you swap the u and v. Yeah, okay. So then what did I want to say? Yes, and it's possible to deduce from this that this P is a Kaminer group, right? So P is Kaminer. I said that already, but yeah, no, P is Kaminer. And so you can get, yes, and yeah, the other thing is that you can get I had this, at the beginning you remember I had this A and the B acting on the W. And so you can also have an A and a B here. There's U and V to the A. I can apply an A, and you see that in here, sigma it respects all the field operations. So this I'm going to apply a field automorphism to everything. Okay, and then things will still work. So I'm going to take U to the P and V to the P, which is just these are field automorphisms. And in fact, it shouldn't. Sorry, let me call this X, not V, because that's what I was calling before. And the other thing is that there's also one like B, U and X to the B is then going to be BU, so you multiply by B. And if you look at what happens here, what you want to do is to multiply by B to the P to the N plus P. Let me get this right. P to the N plus 1, sorry, P to the N plus 1 times X. And if you look at how this you'll discover that A and B are automorphisms of this group, this Kaminer group. Right? There's some work to do, which I'm not going to go into. So these are automorphisms. So we get so A equals A and B equals B are contained in the automorphism group of P, and they behave so B to the A equals B to the P, and they act on W in the same way as they did before. Right? So in this way, you can get you get not only the then there's the question about how do I get an extra special group out of that. Let me just say this. I think it's too. I'm getting. It's getting too complicated. If you look at how the A acts on the Z, right? Now you remember that. So I started out with a field of order P to the 2n, and I had the field of order P to the n underneath. Okay, and if you look at how how the A acts on the Z, which is the you can discover that there is a basis of Z which is which has size n, right? Size n, and A has the group A is cyclic order n, and you can find a basis which is permuted cyclically by this A. Okay, and you know, if you think about it, that's pretty plausible, and then it's true anyway, right? And so you can then take. So that means once you have this basis permuted by A, if you take the sum of all those bases, or rather if you take the differences of those basis elements, they span a subgroup like this Z. I have this subgroup of index P in the P dashed, and so I get an extra special group from that. All right. So that works. All right. So in other words, there is a subgroup Z less than P dashed with P dashed over Z as order P.
But Rex, this Z is not the same as that one.
It is the same.
Are the same?
It is the same. It is the same Z, right? Oh no! Sorry, no. Yes, no. Of course, you're absolutely right. So nonsense. No. So P dashed is the Z, isn't it? So I have to call it Z0. I'm afraid. You're right. Sorry. So P dashed over Z0 is P. So it's the P dash which is what I call Z. Right? Sorry. Thank you. And so then so P over Z, what should I call it? P over Z naught is extra special. And the A and the B still act on it. All right, so I get something very like what I had. You remember the group I had right at the beginning? I had the A and the B acting on an elementary B and W. Well, that's what I have now. I have this W with A and the B acting on it, but this time it has a subgroup of order P underneath. So I get an extra special group with this kind of process. P over Z and A and B still act on P over Z on P over Z. And in fact, so that means, and so you can work out, you can find the automorphism group, for example, of this extra special, of this subgroup with the extra special group, and you can find out, because you have this kind of the formula for the action, the formula for how to multiply elements, and how and for the action of A and B, you can calculate with them, and you can find out, for example, the automorphism group of this, perhaps if you have B acting on it, I said that restricts the number of automorphisms. Now, perhaps I should say that this is one construction we did. To start with, it only applies when P is odd, right? And secondly, you might want also to have an extra special group like the thing with the X, Y, and Z, with the zero subgroups of the general linear group, and where there's things acting on the X and the Y separately. It's not the B doesn't act on the whole of the W, but on the two halves, if you like. And so so you need to have a similar construction for that, and also similar constructions again for the prime 2, which is different for extra special groups always. But so this is kind of an example of one kind of calculation you can do. Yes, I'm nearly coming to an end. Yes. Now, let me mention there are various things about Kaminer groups which are not known. Now, if you like, here I just talked about Kaminer groups as a way into extra special groups, and that is perhaps the most interesting thing about them. But they're fascinating in themselves, and I can't resist, I'm afraid, mentioning some properties and questions about Kaminer groups. So these are things discovered by Mann and Skopler, and to some extent myself. The first, so suppose key is Kaminer. Let's suppose P is a Kaminer group. So just remind you again what that was. That means that every element, so if you fix an element outside P dashed, right, you take any fixed G outside P dashed, then every element of the commutator subgroup has to be expressible as a commutator with G, one of the components, right? So that's a strong condition. Now then, well, first of all, P4 is 1, that there are no Kaminer groups of class 4. Now, that was in a paper by myself in Scotland. That's the only place where I come into it at all, really. And it's hard to understand the proof. I mean, I believe it's true, but it's peculiar. It's kind of mysterious exactly why it's true, but it's apparently true. Now, so other things which kind of come before that. First of all, so let's look at groups of class 3. See, I'd really be concerned with groups of class 2 over here. And as I said, they're really the most interesting ones, probably, because they lead to the extra special groups. But let's still look at groups of class 3 just for fun. So then, now let me make sure I have this, yes. Well, in fact, the P to the P is not actually only contained in P dash, it's actually contained in P3. So it goes 2 steps down and that was Mann's principal contribution, I think. So what you have here is a group of class 2 of exponent P, and so that P has to be odd for that to happen. So P is odd. So if you're looking at groups of class 3, the prime cannot be 2. And also, actually, the n, you remember I had this, so the P over P dash was of dimension 2n. Now, in fact, what you can deduce from messing around with what happens is that the n has to be even as well. Right, n is even. So P over P dashed has dimension divisible by 4. Right, it has dimension 2n and n is even. Has dimension divisible. And another thing is that now also P3 is less than P with a 3n over 2. Now that's a very peculiar result. Let me get this right. And if P3 is bigger than or equal to p to the n, then p over p3 is actually isomorphic to this pf, this group. Well, so I don't know if you've probably forgotten about pf. Pf is this Zilov subgroup of the field of order of GL3f, right? So it was this very easy group where you had x, y, and z, and whatever it was. You could write down the thing. And so if P3 has size bigger than or equal to P to the n, then you actually know exactly what P over P2 has to be. And so, I mean, the question really is, which we don't know the answer is, what can P... We found examples of groups where this P3 has order P to the n. But I don't think we have an example of anything bigger than P to the n. And so what is this, is there something better than that going on? Yeah, perhaps I should say MacDonald actually wrote down, claimed that he could prove that P3 is less than P to the n, or less than or equal to P to the n. But Skopel discovered that he made an easy mistake. He'd written one of his inequalities the wrong way around. Instead of less than or equal to, he'd written bigger than or equal to, or whatever it was. And so his proof didn't prove what he said it would. But this seems to be true. And as I said, the fact that it's strictly less than is very odd, seems to me. In every other case, it's been bigger than or equal to or greater than. So we have examples where P3 is equal to P to the n, but I don't think we have examples of anything bigger than that. And so there's Now let me just say something without writing anything down anymore now, because I've gone on too long already. I got a message from a man called Des McHale, who is an Irish mathematician, again of a similar age to me, perhaps a bit younger even. And he's rather peculiar interests. A lot about kind of automorphism groups of finite groups. And he was asking about groups, so a finite soluble group, let's take the soluble groups, in which the automorphism group is smaller than the group, right? The automorphism group, the order of the automorphism group is less than the order of the group. Now, it so happens that Maria Dolores, Arnie Feldman, and I, as I said, had worked out some automorphism groups of these extra special groups. And we already had an example of that happening. A group of order 1500, whose automorphism group had order 1200, right? And this was an extra special. This was a group. Was it extra special? Yes, it was. It was it's a cyclic group acting on an extra special group. Right? The extra special group was order 5 cubed, if I remember rightly. Right? Is that not possible? No, maybe it wasn't. I can't swear to that now. And as I think Des McHale, this Irishman, he has a kind of various ex pupils of his. One of which is a man called Heffernan, another Irishman who I think is working in Sweden. And Des McHale had got Heffernan to look through on the internet for examples, small groups, and work out the automorphism group and see is it less than the size of the original group. Okay? And I think he had already been looking up to about kind of 500 odd, and had found no such groups. And Des McHale, I think, was surprised to see this group of over 1500, which we had a group of 1500 with an automorphism group of over 1200. Okay? And so he talked to Heffernan, his ex-student, and persuaded him to look a bit further. And Heffernan found a group of order 7 times 2 to the 7, which is 890 odd. It's a little bit less than 900. And the automorphism group was half the size of the group. Now there was a center of order 2, and you factored that, and the automorphism group was just the inner automorphisms. Now, so he told me this, and we were looking at this, and as I said, it's 7 by 2 to the 7. Now 7 is 2 cubed minus 1, right? So 7 is 8 minus 1. And so if you have a field of order 2 cubed, then the multiplicative group has order 7. So it's pretty clear that what you have is a group of order 7 acting on elementary groups of order 2 cubed. And it's also, if you think about it for a minute, it's pretty likely that what you have is a group of class 3. Okay? You have this field of order 2 cubed has p over p dashed, and another copy of the field have p over p3, and then p3 is the center of the whole thing. Okay? And so the challenge was to find a construction of that group. And we have, I think, succeeded in doing that. And the reason why I'm going on about it so long, I'm sorry about this now, is because that is a group of class 3, whereas all the examples which I had over here were just of class 2. And in fact, constructing groups of class 3, the associative law, I want to do similar things with kind of, biadditive maps and things as I had before. And it seems surprisingly difficult to get it to the associative law. Doesn't seem to be, it's quite easy to do in class 2, because it just had this biadditive map. In class 3, it seems to be much more complicated, a good deal more complicated. But we did succeed in finding an example, and so that kind of gives me hope that perhaps we'll be able to look at Kaminer groups of class 3, possibly, and get ahead. So I'm sorry I've gone on much too long, and that's the end of it.
Any question? ¿Alguna pregunta? ¿Comments? Es que no sé cómo funciona.
No, tenemos con la de YouTube.
Yes, I should have been standing in the middle. Shouldn't I? Sorry.
No sé cómo funciona.
I've forgotten about that now.
Bueno, déjalo, igual.
No sé si podrán hablar.
Pues déjalo.
Y es que no sé ni quién está conectado.
Vale, pues déjalo.
I think I do not want to see myself. I think I do not want to see myself.
¿Mi cuestión o alguna pregunta? A ver, interesting.
Thank you. Well, thank you very much for coming. Thank you very much for coming to listen to it.